Welcome, we're live.
All right, so welcome to our second hangout of this iteration of Interastra, and thanks to everybody who's showed up. Um, if it looks like it's a little dark today, that's because I'm sitting in Berlin, Germany, and it gets dark very early around here. Um, and so we're going to do the same thing we do on these hangouts. We're going to have people introduce themselves. We have a bunch of people from all over the world say something about themselves and about the course if they'd like to, and then bring up a topic for conversation. We'll try to address that. And then we'll go through it. If we have time, we have a bunch of questions that people have asked. And if anybody has more questions, then they can post to that questions and answers, right? I think.
Yes, Q&A.
And we will see those questions, and we can respond to them as we have time. And then I'll remind everybody who's on the Hangout that when they're not speaking, they should probably mute their microphone, otherwise their background noise comes through. And then unmute yourself when it's your turn to speak. And perhaps can we start with, I don't know, by my order. Simon, do you want to start us off?
How are you? My name is Simon Stewart. I'm a 64-year-old. I'm a scientist by trade, a chemist. I've done very little physics, and in the last few years I've tried to teach myself some physics, and your course is a fantastic opportunity.
Thank you. I'm glad you're enjoying it. Did you have a topic you wanted to bring up, or a question, or?
I've wondered for quite a while. They talk about further out in the universe that you look, the faster and faster it appears that things are moving away from us. I wanted to know how they compensate for the matter being between its source and coming to us at very low density to take that into account, because I thought it redshifted light, and how would they compensate? That's what I'm on about.
That's a very good question, and I want to first apologize to you as a chemist. You will have noticed that there are lots of places in this class where chemistry would have been relevant, and the reason I didn't say much about this is because I know even less chemistry than I do astronomy, about none, and so that's a valid, that's a good opportunity for that. But what you're pointing out is very correct. When we look at an object, we know that if there's dust clouds in between, then because the dust preferentially scatters blue light, we are more likely to see redder. The things we look at will appear redder. It's called reddening. There's a expression for this reddening factor. And of course, the farther an object is, assuming a roughly random distribution of dust, the more dust clouds will probably be between it and Earth. And so indeed, just on the basis of dust, without expansion, distant objects will appear redder. This is an issue which in some circumstances needs to be corrected, and you do calibrations of this. So we have a pretty good image, a sense of this reddening factor. But before that, the way we measure redshifts primarily is using spectral lines. And when you have a spectral line, that wavelength is determined. What intermittent reddening, what an intervening dust cloud might do, is it might change the intensities of different lines. It might scatter the blue more than the red, so the blue will lose more intensity. But it doesn't actually frequency shift. Scattered light is scattered at the same wavelength at which it was received. When we say it's reddening, it just means that of a beam of, on average, white light, the same amount of blue, green, and red, more blue will scatter, so more red will survive. But each individual photon that penetrates, that isn't scattered, maintains the same wavelength that it had coming in. So that if you have a sodium line with a very sharply defined wavelength, scattering won't change that wavelength. Scattering is an elastic process, pretty much. And so when we observe a shifted spectral line, that is not due to anything in the intermediate medium. It is just the Doppler or the cosmological redshift, and we'll talk about the distinction between these two and the way in which they're the same in the last weeks of the class when we talk about kinematics of cosmology. Is that the question you were asking?
That's close. Is there a gravitational effect, even with small amounts over a long distance, to affect the redshift?
So that's we're talking about a gravitational redshift.
Yes,
so,
but that's
absolutely.
Yeah.
There are two kinds of gravitational effects. One, as we will discuss, is the cosmological effect. That's essentially what you're measuring. The best way to think of the redshift that is in popular descriptions associated with having things moving away from us. It's better, it turns out, and where both descriptions are applicable, they coincide, and at large distances, thinking of it as a gravitational redshift is a better way to think about it, and we'll talk about that. And so, yes, there is that's the global gravitational effect. Superposed on that, there can be local effects, which have to do with moving in the vicinity of actual mass concentrations, not the average homogeneous uniform mass density of the universe. Those, by and large, do not cause a big shift because typically if in between some distant galaxy or a quasar or something and us is, say, a galaxy cluster, then our photon starts very far from the galaxy cluster, falls towards it, and is accelerated, or in other words, doesn't change speed, but is blue shifted as it falls in, and then red shifted as it climbs out. And to a good approximation, the redshift is the gravitational potential. If you start very far from something at potential approximately 0, you come very close, you get blue shifted, you move far back off to infinity, you're redshifted back to exactly the original wavelength. So the only time in which there's a net effect is if the radiation was emitted from the vicinity of a very massive object. And then we see that. But other than that, other than the local effect, all the local effects in between us pretty much get washed out.
Okay. Okay, that's very good. Thank you.
That's a very good question. Thank you. Let's see.
Okay.
Let's see if we can have someone else introduce themselves. Let's try, I don't know, Roberto will have to do it by text. So let us give a chance. Justin, I don't have everybody's names for some reason, so can you call, because I'm going to get it wrong.
Sure. Pranav, do you want to unmute yourself and introduce yourself?
I'm Pranav. I'm a software engineer from India. So I'm 21 years old. I've read so many astrometers before, but what I was missing was the physics and chemistry, physics and math part of it. So this course has been really helpful. So thanks for putting up this. Something I want to add to the previous question was you said the wavelength of the absorption lines don't change, something like that, but I wasn't very clear about that. In the last question, you said if there's a sodium absorption line, it doesn't change its characteristic wavelength. I wasn't clear about that.
Okay, so thanks for joining us. There are several things that I could have meant by that statement, and I guess I meant all of them. One of the statements is that there's this fundamental principle that we assume until proven otherwise, and it's held up very well, that on Earth as in heaven, in other words, the sodium atoms in a distant supernova are identical physically to the sodium atoms here. And so they emit at the characteristic wavelengths of sodium. And if we observe the emissions from those same sodium atoms at some other wavelength, then it's due to some effect associated to either motion or this cosmological expansion that we'll talk about, or a gravitational redshift, or some combination of the above. What I was saying was, oh, go ahead.
Suppose something is redshifted too far from its actual location. How do we distinguish it from something that is closer to its current location?
That is a very good question, and it isn't true that as observed, lines can be redshifted, and the farther something is, the more redshift we have, and that makes sometimes the identification challenging. And I will mention in the last week at least one example, the discovery of quasars, where spectral lines were found that were thought to be unfamiliar. Nobody knew, oh, some new material like helium. And then it was only after somebody looked very closely and took into account the possibility that this light was a very intense and very distant source and allowed for the possibility of a redshift of 2 or something, that they realized that with a redshift of 2, it matches hydrogen. So they were seeing hydrogen lines shifted, and nobody thought about this. The way you nail down very precisely the identification of which spectral lines you are seeing when they appear redshifted by a significant amount is that if you recall, one of the beautiful things of the Doppler and of the gravitational redshift factor is that the shift is by an overall factor of some function of V over C. In other words, all wavelengths are redshifted or blue shifted by the same factor. And the ratios of wavelengths are therefore exactly unchanged, precisely to all of it. This is not an approximation. And so when we identify the chemical fingerprints of, say, hydrogen, we have a few very prominent hydrogen lines, and the ratios of their wavelengths are known to very high precision. And so if you find a collection of 4 lines with exactly those ratios, but shifted to the red, you're very likely to have found hydrogen. And yeah, you do cross-checks with the relative intensities and so on, but it's essentially, the crucial point is that the ratios don't change. And that's how the identification is made. That's a very good question.
Thanks.
Thank you. Try someone else?
Yeah, I was going to say that I think of those spectral lines as like a barcode for an element, and if you see that barcode pattern, no matter where you see it or how far to the left or the right it is, it's still that element. It represents that element. Leonardo, do you want to unmute and introduce yourself?
Hello, everyone.
Hi there.
Can you hear me?
Yes, we can. Go ahead.
Oh, my name is Leonardo. I'm from Veracruz, Mexico. I am a theater actor, and this is my first course in astronomy. And I have been taking a few courses before in Coursera, and I think in this course is a great opportunity to recall or have a tour about 2 centuries or more of history and a lot of physics and a lot of work of many people. And I think it is, at least for me, a little intense, but it is a lot of fun. I think every topic is almost a science, and you have a lot of details to have fun.
Well, I'm glad.
And so,
It can't be, I mean, I agree this is very intense. There's just a lot of good stuff, but it can't be more intense than, the last month before a theater production. I've seen that happen. So you should be used to this level of intensity.
well, it seems it is
Oh, wow.
intense too. So I have a question.
Shoot.
Do you think that the study of the universe, I mean, other stars, other planets, could help the humanity to realize that a planet like Earth, able to support life, is rare and can avoid to destroy it?
Well, that is a very good question, and let me say before I say anything about this that it's not a physics question, and so I have an opinion like everybody else, but it's a layman's opinion. I'm not an expert on this question. Actually, nobody is a real expert. Nobody really understands. If there's one thing nobody understands, it's humanity.
Yeah.
And I think that. But I can answer some of the technical aspects first, and it's whether studying astronomy tells you that planets like Earth capable of sustaining life are rare, or on the contrary tells you that they are common, depends exactly how you phrase the answer or the question, because we live in a huge galaxy with a trillion stars. And what we've discovered is that it's very likely that most of them have planets, and therefore it's quite likely that a small fraction of those, but a small fraction of a trillion is still a big number, actually have planets that might be able to sustain life. And there have been recent exciting discoveries of planets that superficially, at the level that we can check, might actually be candidates for exactly such a thing. And so maybe there are, only 10 million life-sustaining planets in the galaxy. Is that rare or common? I don't know. That depends on how you use the word. What is true about all of these planets, billion, 10 million, 100 billion, whatever number, is that all of them are completely inaccessible to us. And they're inaccessible with current technology and with most of the possibilities for human motion that we can contemplate. And so pretty much our future as a species is tied to this planet, at least in some foreseeable future. Now, it is equally true that studying astronomy teaches us things about this planet, like in 2 billion years, this planet may not be habitable. It is kind of daunting to think of humanity surviving another 2 billion years given our performance over the past 1,000. But if we were to survive 2 billion years, then we'd have to figure out something about how to survive past habitability of Earth. And so I think to the actual precise point of how crucial it is for us to understand that if we make Earth uninhabitable, then we will be gone as a species, astronomy doesn't change that equation in any fundamental way. It sometimes helps. There was this great hope in the last century when we first had people in space looking down at Earth and getting these pictures of the beautiful blue marble, that somehow this would make an emotional shift in all of us and make us realize the unity of the planet and wars would cease and we'd all get behind protecting our planet. Needless to say, the history of the past half a century has not completely borne out those hopes. That's no reason to get up on them. I think one way to think about it is we need whatever we can to help us realize those important facts. And if astronomy can be leveraged to that end, then that's a wonderful thing to do with it. That's certainly a good idea. And to me, if nothing else, look at all the beautiful work that we've been studying and all these brilliant ideas that all these great people have had and all this beautiful culture in place. Wouldn't it be a waste to throw all that away because we're not careful? So if nothing else, just the intellectual side of it appeals to me. But again, this is the contribution of one guy from Durham. That's all I have on that one. It's a good question.
Okay.
Thank you.
Thank you.
I think Roberto was asking a question, and since he can't
Yes, I was going to suggest that.
repeat that. So Roberto is asking, is there a certain proof that the universe is homogeneous and isotropic? What about if it is not? And that is a wonderful question, because the answer, like with most wonderful questions, is, well, sort of. We know that to a very high accuracy, the universe, as we measure it, is homogeneous and isotropic. And the way we know this is by doing things like measuring the numbers of galaxies we see at different distances and different directions, and noticing that there is not a direction where there are more galaxies than others, and noticing that there are that the distribution of galaxies, and there's a graph that we will show at some point in the coming week, I believe, or the week after, that shows that at distances of more than about 100 megaparsecs, the distribution of objects in the universe is roughly homogeneous. There's basically, knowing there is a galaxy, say here, makes it highly likely that there will be another galaxy nearby because galaxies come in clusters. But by the time you look 100 megaparsecs away, the knowing there's a galaxy here tells you nothing about the probability of having a galaxy there. So that's what we mean by homogeneous distribution. And the same thing is true for isotropy. That said, there may be, at some higher order, at some higher precision, both large-scale structure beyond 100 megaparsec that is too fine for us to have detected in these statistical surveys yet, and in homogeneity. And in fact, there is, at any given time, there will be a few theoretical physicists working on constructing what is called a very special relativity, which is the theory of relativity, or the theory of particle interactions in the presence of a preferred direction. So you have general relativity, where all inertial frames are considered and relative acceleration is allowed. And you have special relativity, where you have a preferred sort of zero acceleration frame and there's no gravity, and so you only have inertial observers. And then you have very special relativity, where you also have a preferred direction, and so the symmetry is only under rotations around that direction. You get a partial. The Lorentz transformations are no longer symmetries of that universe because there's a direction selected out. And if you make the violation of rotational invariance small enough, then we would not have detected it yet. And this could be a local effect that due to some effect in our neighborhood, or some global effect. So the answer is always that, to very good precision, we measure a homogeneous and isotropic universe. And so we know that violations of this in the large scale have to be quite small. We have very good constraints on them. But of course, it's also true that the universe is not homogeneous and isotropic. I am here, and I am not there, and Earth is here, and the galaxy, the Milky Way, is here. And that's an inhomogeneity. So we don't mean literally homogeneous. We mean that on large scales, when you average, it's to a very good approximation homogeneous, and then there are small perturbations in homogeneities riding along, but they are at tiny fractions of, at best, one per a few parts per 100,000 or a few parts per million. And then we keep putting bounds on that. And we'll talk more about all these cosmological topics, obviously, in the last 2 weeks, and hopefully that'll help a little bit.
Great, thanks, Roberto. Ivana, do you want to unmute yourself and introduce?
Hello, I'm Ivana. I'm from Croatia. I'm an artist, but I also sometimes work as science illustrator, so I try to keep up with the scientific courses. And I was wondering if you would like to share something about your research, about the role of geometry in physics.
Oh boy, that's a big question. I mean, the answer obviously is yes. I can share an anecdote, though. When my daughter was 12, she's now grown, but when she was 12 at school, she was asked to describe a scientist. All the kids had to write a little essay. What do you think about a scientist? And my daughter's answer was, scientist is someone that if you ask them a question, you get a long answer. And so if I actually let myself go on describing my research, that would eat up more than this Hangout. And in particular, at the end of the course, I actually could not resist recording a sort of informal, rather long lecture video on string theory. So that'll be part of my answer. But there are several aspects of geometry and physics that interest me. One is, of course, that in the context of general relativity, the shape of space is governed by physics. It's determined by gravitation. And we typically think of that as sort of ripples in an otherwise homogeneous space. You have sort of a uniform, homogeneous, roughly flat space, and then there's a dimple where the sun is, because the sun is a massive object. But you can think of more sophisticated geometries that can arise, and studying them with Einstein's equations is difficult but possible. And in particular, physicists get especially excited. I think we talked about this a little bit in the black hole scenario, where there are singularities. It's a property of general relativity that we create singularities. And near singularities, the geometry is changing very rapidly on small distance, over small distances. There's a place at the singularity, at a singular place, where something is very different, even if you're very nearby. Einstein's theory breaks down. We have this idea of using string theory to describe it. And in the context of string theory, we have managed to produce sort of geometrical interpretations of many aspects of physics, both gravitation, but also the kind of weak or strong nuclear interactions, the gauge symmetries of nature, are in string theory implemented geometrically. And so you can, in the geometry of some, in some circumstances, of some kind of space, and so studying the geometry of those spaces teaches us about physical principles. And it's been my good fortune to be sort of working in a field and at a time where there's been this amazing interplay between learning more about the geometry, the geometric structures of some kinds of mathematical objects, and realizing that if those objects are invoked as parts of space, part of the properties of space in which a string theory is defined, in which strings propagate, then these geometrical properties determine some physical properties of the universe that those strings describe. And that thinking in this dual way, geometry on the one hand and physics on the other, has allowed us both to learn things about physics we did not know, and to learn actually things about geometry, solve open problems in geometry by first translating them to physics and then solving the physics problem and pulling back the solution. And so there's been this great interplay between mathematicians and physicists, and walking the line in the middle has been a lot of fun. So this is a pretty general. I haven't given a very specific answer, but it's hard without getting too technical.
Thank you, Ivana. Hector, do you want to unmute and introduce yourself?
Sure. I'm Hector Garcidueñas from Mexico City. I'm a mechanical and electrical engineer, so I've always had a little interest into physics, and it has been great to deepen that greatly with this course. So I have a comment and a question. Something I've liked a lot from the way you've given the course is that you've also taught us a little bit through the history of how we've discovered how to measure distances, or how we have our knowledge of the atom has progressed. We've managed to learn a lot from that discourse. So my question is a little bit to the future, asking you to speculate a little bit, say in 5 or 10 years, what are some of those very interesting questions that you think we're on the very verge of answering?
Wow. Okay, that's an excellent question. That's very exciting for me to speculate on. But of course, you realize I'm speculating. And I will restrict myself to the very narrow fields that I really am knowledgeable about. So I'll talk about particle physics. And from my point of view, from that point of view, I think the things that we're most likely to understand, or that we hope to understand in the next decade or so, first and foremost, we would really like to know what dark matter is, and what it's made of, how the dynamics of these particles, if that is what they are, what kind of dynamics they obey, what their spectrum is, what their properties are. And many people feel that we are in some sense on the verge of maybe being able to do this. Now, this depends on all kinds of assumptions about what we think it might be. If we're very wrong, we might not find anything. But there are ongoing experiments searching for direct detections of dark matter. There are ongoing theoretical studies of various aspects of what this could be. And I'd say that this is sort of in the list of experimentally discovered but theoretically unexplained properties of the universe, on which the Higgs particle would have been the #1 item up until 2 years ago. Dark matter is now one of the leading candidates. And it is hoped by me and by many others that if we discover that there are really dark matter particles, and manage to elucidate something about their nature, then it will also teach us something about the bits of physics that we have not even yet addressed. There are open questions in the standard model of particle physics, and we don't have any experimental hints, really, on what types of answers we should be looking for to those questions. And in some sense, what the nature of dark matter is might be our best chance and a hint for what the physics is at energies beyond those at which the standard model is applicable. So I'd say that probably comes first. A second question on which we would like to have some understanding is dark energy. So those are two, we'll talk about both of those in the cosmology section of the class, but those are two phenomena experimentally verified to some extent with no theoretical understanding. And both theorists and experimentalists are furiously working to try to get to the point where we know enough about the nature of the thing to be able to validate a theory. And I think from this point of view, that is one of the things that is going to be very exciting. Obviously, in other fields, things like the discovery of planets that could harbor life, or even more excitingly, planets that do harbor life. So a big oxygen-rich atmosphere somewhere. That would be exciting, and one could go back to the question about how this would impact our sociology and would it make us less stupid as a species. One can only hope. But those are the two that immediately jump out at me. There are other hopes, things I would like to hope that we will understand, but I don't have as concrete a path to getting there as with say, dark matter, which I hope we will understand. I mean, it seems hopeful, but not crazy to think that in a decade we might know something about that.
Great. Thanks, Hector.
Thank you.
Abdesamad, would you like to introduce yourself?
Yes. Hi, everybody. My name is Abdesamad Motasim. I am talking to you from Rabat, the capital of Morocco. So first of all, I want to thank you very much for this course. It's a very wonderful course, outstanding. It has a very rich information there, a lot of learning exercises. So thank you very much. And I took this course before. This is the third time I'm taking the course. So this is another advantage of the MOOC, because taking a learning and course again and again will end up by knowing much about it and be some sort of expert in the subject. This is in addition to the fact I love astronomy. I work with some teenagers here in my city in a club, an astronomical club. So I'm trying to advise them and to work with them to understand this wonderful area of knowledge. So I have 6 questions.
You're good. Why don't you start with one and then we'll see where we go. How's that?
Yes. 5 of them I had written them for yesterday. So probably you might be aware of these questions. So I will pick one of them. So the first one, I will talk about the moon. The moon craters are mostly present on the far side of the moon, which means that there was a huge peaks in the past that transfer momentum to the moon orbit, and that the moon should move towards Earth. And this is contradictory with the fact we learn in the course when you say that the moon was near the Earth at 10 to 74 meters and moved away to its current orbit. So I want to understand this contradiction.
Okay, thank you. It's true, and I hope I mentioned this at some point in the lectures, that there is an interesting asymmetry between the near side of the moon and the far side of the moon, both in terms of the surface features. And it is indeed true that we see more craters on the far side of the moon than on the near side of the moon. This is typically interpreted somewhat differently than what you suggested. we typically think of it as just being due to the fact that a non-trivial part of the near side of the moon is covered by these maria, these lava flows, and there are no maria on the far side of the moon. And these lava flows, of course, whenever you have one of these craters filling with magma, this erases all previous cratering activity, right? Because it just fills in all the holes, and you start from tabula rasa, we start from a very flat surface, and then you only see modern cratering. So the maria are not cratered much, whereas the far side of the moon is all highlands. It's all untouched and unresurfaced. And so in some sense, and the maria we interpret typically as the results of particularly violent collisions so violent that they cracked the lunar crust and allowed magma to come out and seep out to the surface. And so this is typically interpreted as telling us that there have been more large collisions on the near side of the moon than on the far side of the moon. Also not something that's very well understood. But there are also deeper differences. There are differences, we think that there's an asymmetry in the distribution of mass in the moon. That actually the near side is somewhat, the mass is a little bit lopsided, shifted towards the near side. And I think those are very poorly understood, and I certainly don't know a valid answer. The statement that these collisions of objects with the moon would have pushed the moon towards the Earth, I think this is a little bit confusing to me because while there have been some pretty massive collisions, massive enough to, large enough and violent enough to crack the crust, the total momentum carried by such an object coming hard enough in to crack the lunar crust to make a mare, is actually pretty insignificant compared to the moon's momentum in its orbit around the Earth. So if you compare something falling onto the moon, we did the calculation for something falling onto the Earth, and if you can take our asteroid from that homework set and make it fall onto the moon, and you can compute the momentum it will have upon impact in the moon's frame, and you can compare that to the total momentum that the moon has as observed in Earth's frame by taking the mass of the moon times the speed with which it orbits. And that gives you a sense for how much the moon's orbit will be changed, by what fraction, due to this collision, and you will find that this is pretty negligible. So these collisions change the structure of the moon, the very violent ones, but they don't really have a serious effect on its orbit. And so I don't think that there's a very strong contradiction there, is how I would answer that question. I hope that answers what you were asking. I was trying.
Yes. So the second question I have is in lecture 5.8, first quiz, you say that water was brought up to Earth by comets. And we all know that there was a mission to a comet, which is called Rosetta. And this is, from what I know, that they deny the existence of any water on Cherry comet. So how do you explain this?
Well, again, I want to make that a little bit more precise. You're absolutely correct. The Rosetta results, of course, came in after that lecture was recorded. So they were certainly not part of the information that I had when I made that statement. But summarize was, and to a large extent, this where it came, from which it could approach this in the form of ice, is still the leading theory as I am. This that I can, but I don't actually do research there. And I think what the Rosetta mission discovered is not that there's water on the comet, but actually that the isotopic composition of the water they did find on the comet appears to not quite match what we find on Earth. And they said that this
Ronan?
I froze.
Ronan, sorry to interrupt. We're having a little trouble receiving your feed right now, so we're not getting your answer very well.
I understand. Can you hear me now? I apologize.
I can hear you. It's still a little bit scrambly.
Yeah, so is the way I hear you, and I didn't understand that it was me. Let me see what I can do to improve things. Does this are we any better now?
Not really, no.
That is an issue, and I don't know how to fix it. This is what happens when you improvise with.
Yeah. Right now we don't have any video motion, or I don't have any video motion, and your audio is. Oh, it started to move again. Let's see here if it can catch up a little bit. But for most of your answer, we were not getting your response. It was scrambled audio. Well, okay, we're having our tech challenge for the day. Regarding the water ice question, I think Ronan's going to pop out and pop back in and see if he can have a fresher feed. But regarding the water ice question, I think that's interesting new information that we're learning about with Rosetta and with comets, and as we get more adept at reaching comets with some of these missions, we'll get to have a better statistical understanding of that and find out whether water ice not appearing on that particular comet is unusual or the trend, and start to have to really refine what our theories are for where water comes from in the solar system and everything. And
Christine, are you going to answer my other questions by email? Probably it's if you don't have.
Well, if we can get Ronan back in, Abdessamed, I was actually going to have him answer some questions that other students had posted as well, so that some other people can have a chance to get some response from him. And maybe even Shubham, who came in later on in the Hangout, might have a question here that he would like to ask too, once we have a chance. Hopefully we can get Ronan back in again before too long.
I'm keen to have a meeting between us, 2 or 3 of us, to discuss these questions, if you will, if you have time. So feel free to vote this to you.
Shubham, do you want to unmute yourself and maybe introduce yourself?
Yeah, hi, I'm Shubham Jain, and I'm based out of India and working for the Boston Consulting Group. I'm an engineer in background, and also sorry to the complete group because I couldn't make it in time and I had to join in later.
No problem.
So the question that I had for the professor was, I just wanted to take his opinion in terms of what would be the recommended courses after I complete this course of Coursera. So how do I take my learning forward?
Right. Well, if we get him back in again, I will certainly have him respond to it as well. But what I would say for you, actually, is in this question, is that your fellow students might actually have more valuable input about this in some ways than Ronan might even have, because I'm sure that his path was more attending a university, and in the course of that, you go to graduate school, and then like that tends to be the path into being a physics professor, for example, and that might not be the direction or the goal that you're necessarily looking at. So that there may be other students who have taken this course and said, oh, look, there's these other astronomy courses that I thought were really good. Something like that might be helpful for you. The one that I know of that I've actually looked at was the Galaxies and Cosmology course that I think is given by Caltech on Coursera, which is a very interesting and challenging course that takes it to a higher mathematical level for the galaxy and cosmology part of it, which will be the next 3 weeks in this course. So if you get a flavor for these next 3 weeks and you think that's great, then you might look for that Galaxies and Cosmology course from Caltech on Coursera.
Oh, okay, sure. I'll surely check that.
I do know that there are several other astronomy-related ones as well. There's a Science of the Solar System course. There's also a astrobiology course. And I've heard good things from students who have taken both of those courses too.
Okay, can you come again with the second one? Science of the Solar System, and the second one would be?
And an astrobiology course.
Okay.
So speculating about what life would be like in planets around other solar systems.
Oh, that'll be great. That's pretty much it from my side.
Say something?
Sorry, go ahead.
I was going to suggest that one of the greatest teachers is the history of physics. If you haven't got a strong maths background, it's possible to learn a lot following looking at the history of the developments, and the concepts are provided very, very clearly as you follow physics as it's gone over the last 2 or 3 centuries. And there's wonderful material that's not in courses like this, but in books. Many videos. Richard Feynman probably was one of the best people back, 30, 40, 50 years. And no one in his own way has got also that ability to explain complicated things very simply. And that is the best thing about listening to him in his talks. But as people want to learn about the physics in an amateurish way, the way I do it, history is a fantastic teacher.
Yeah, I would agree with Simon too, and I second his recommendation of Richard Feynman. He has a real gift for describing and conveying ideas without getting extremely complicated.
That's right, and there are on the internet available, one way or another, some fantastic talks he and a number of other people have given, and they have the ability to explain complicated physics in a layman's terms. It's a real treasure when you find them. Mm-hmm. If you don't have strong mathematics, it is hard to follow lots of the explanations. Anyway, thank you. I'll turn off.
Thanks for that, Simon.
Thanks, Simon.
Well, I've heard from Ronan via email, but he still does not seem to be able to get into the course. So We might have a default ending to our Hangout for today then.
I think he just joined.
Oh, hey, there we go. We got you back. Thank goodness.
I'm sorry.
You had about 30 more seconds, and I was going to shut you down.
Sorry, I had to move. I apologize. This is what I get for improvising. All right. I'm back now. It seems that everything is working. Phew. I apologize to everybody for the technical glitch. So we have one person who didn't get to ask, right?
Yes, we were just talking to Shabam. He had a question about what should he do next to help further his astronomy learning.
Oh boy. So
we talked with him a little bit. I gave him some of the other Coursera classes that exist on astronomy.
Exactly.
And we were also, Simon made a good recommendation of looking at Richard Feynman, not necessarily for the astronomy, because that's not his area, but his quality of explanation for physics concepts.
Is incomparable and certainly appreciated by many. There are lots of other good books that talk about astronomy, and especially depending on exactly what part of the material, right? We're covering the entire universe here. There's interesting things at every scale and every size. There are lots of good books and more coming. There are, and I mean, I can't recommend a particular one. Depending on how much math and how technical you want to make it, if you want to take sort of math to the next level and you're comfortable with calculus, then I have a standard answer. There's a standard textbook for astrophysics that covers essentially very much the same material we covered, but very rigorously, and is sort of the gateway book. If you're a astrophysics PhD student, I guess this is the first book you read, and the one that you keep on your shelf. And I can tell you that if you're a theoretical particle physicist who's trying to fake his way through teaching astronomy, that's the book I keep on my shelf. It's a book by Carolyn Ostley, which is this big fat orange book, and I think astrophysicists call it the Big Orange Book. And it's very comprehensive. It is at a level of depth that is sort of 2 levels of detail beyond what we do, and that renders it somewhat extensive, but it covers roughly the same material. And I can say that some bits of the treatment in this class are modified versions of what they do. So, I mean, you'll recognize some things when you read that one. But there are lots between, you can go from that to a huge number of sort of more popular books on various aspects of planetary science and the new discoveries of exoplanets or cosmology that are usually pitched a little less technical than this class. Actually, the precise ground that we are, the level that we're holding in this class is very rare. Sort of doing all the math that you can without calculus, but doing as much as we do without calculus is pretty rare. I don't know an actual book that or a collection that aims. That's sort of our niche. That's what we do. And, so pretty much you have to either dial it back a little bit and get more information, or push it forward a little bit and do a little more, and then there's lots of stuff there. But I guess it's fair to say that I don't know something at exactly this level that goes farther.
So Ronan, I've got a question from Tomer, which is on the Q&A app now, if you can see it.
I can see it, and I'll be happy to answer it. So Tomer asks about the Higgs particle. Where it comes into the picture, and how does it explain the mass of matter? And that is a very good question to ask, and thank you, Tomer. It's not an astronomy question, but it's a particle physics question. And the first, and it's important to answer it because the answer is, well, not really, as usual. There's a little bit of a misconception there. So it is a property of the standard model of particle physics that because of the way we formulate it mathematically, it is necessary that if you study the theory at very high energies, or if equivalently you take a chunk of the stuff that is our universe, the chunk of the universe, and heat it to a very high temperature so that the average energies of whatever particles are flying around there are high energies, then it behaves as though all of the fundamental constituents particles that we list in the standard model, and we've listed many of them in our little growing and burgeoning tables of particles. So the leptons, the muons, the tau, and the electrons, their companion neutrini. And then you add to this 3 or 6 flavors of quarks, depending how you count, and out of which nucleons are made. We had nucleons, but nucleons are not fundamental. We know that they're, in some sense, composed of quarks. And then the force carriers of the weak force, the strong force, or the gluons, carriers of the weak force, the W and Z bosons, and the photon. And all of those particles are massless in some fundamental sense, in the fundamental mathematical formulation of the theory. When we do measurements, however, we discover that some things are not exactly as I just said they are. Photons are indeed massless, but the force carriers, for example, for the weak interaction, the W and the Z bosons, are massive particles. And the way we incorporate what we observe at low temperatures, at the very low temperature of the universe, as massive particles, and whereas fundamentally at high temperatures these behave as massless particles, is something called the Higgs mechanism, and it involves the existence throughout field of space-time, throughout space of a field called the Higgs field, and it is the properties of the Higgs field, or the interactions with this ambient Higgs field, if you want to think about it that way, that are responsible for these particles having a mass. So far, so good. And it is a property of quantum field theory that when you introduce this Higgs field, the mathematical formalism brings along with it a massive spinless particle, which we call the Higgs boson. And this is the one that was recently discovered. And so in some sense, discovering the Higgs boson validated the mathematical theory that underlay it. I should point out that, on the other hand, if we try to measure the mass of a glue particle, a gluon, the carrier of the strong force, or the mass of a quark, we have difficulty because we do not find gluons or quarks as part of the particles we see in nature. In nature, gluons are bound into nucleons and or other hadrons, and free gluons also do not exist. And while they behave at high energies as though they were massless, and they do not acquire a mass through interaction with the Higgs, unlike the quarks, we don't detect them. And this is associated to properties of the strong nuclear force. And the reason I bring this up is that, indeed, the interaction with the Higgs field is responsible for the quarks not being massless. Quarks have some mass. The total mass of the quarks in, say, a proton is less than 0.1% of the mass of the proton. The actual mass of the proton could be thought of as being contained in the color fields, the interaction, the strong interactions between the quarks, and B, if you want, their kinetic energy. They're orbiting each other. So there's some virial relation between these two. But the actual masses of the quarks are only a very tiny fraction of the mass of a proton. And so to say that the Higgs particle is responsible for giving matter mass is stretching the point a little too far. The Higgs particle is responsible for giving mass to W's and Z's, which we rarely see, and electrons, which comprise, as we know, a tiny fraction of the mass of any macroscopic object. Most of the mass of any object is in the nucleons, and the mass of a nucleon is mostly associated to the strong interaction and has nothing to do with the Higgs boson. So how it happens is a mathematical fact, a property of this model called quantum field theory, and its discovery, the discovery of the particle that is predicted by the Higgs phenomenon, was a great triumph of quantum field theory. But to say that it's responsible for, say, the mass of me is a little bit stretching the point. So it's a little bit of a technical answer, but at least I clarified one thing that is often misconstrued, so maybe that was helpful.
Thanks, Ronan. We're getting close to 10 o'clock here.
Yep.
I have one question that I'm going to pop up, and it's from Pranav, but I thought it was an interesting astronomy question for you. So he says, with visual pollution becoming more and more severe year by year, what do you think about the future of sky watching?
Well, I think people will always watch the sky because the fascination is going to be there. All of you are probably looking at the sky, whether you were previously accomplished astronomers like some of our students, or didn't used to look up, but now that you're thinking about this stuff all the time, it's impossible to resist. You know, Venus was at Extension recently and offered beautiful views, and there was no way to walk out at sunset and look west and not see this beautiful big thing and go figure out, oh, that's Venus, I just saw Venus. So people will look up. There is the beginning of awareness, and indeed, there's more of us living on Earth, and we tend to like our streets to be illuminated at night just because it helps us not stumble, if no other reason. And so there will be increasing problems of light pollution. There are some technological improvements that people are making that can help with this. So it turns out that an amazing fraction of the light we use to, say, illuminate our streets, because of technological engineering issues, is actually wasted. It's radiated out to space. All of the light that reflects off clouds or moisture in the atmosphere and makes the sky bright and makes it impossible to see stars. Well, not being able to see stars is, to me, a tragedy. To humanity, in a more practical sense, this represents energy that we produced, or producing energy, as I said, is a misnomer, but whatever, you know what I mean. We harvested and converted to electricity, and probably created greenhouse gases in the process, and wasted the resources that it takes to excavate oil or coal or whatever it is. And now, instead of that light being down, those photons being right here in my eye where they help me see the street, they're up 50 miles in space in the atmosphere where they do nobody any good. So there's every motivation to be more efficient about our lighting, and at the same time, as a nice side product, make the skies beautiful at night again. And there are people who work on such technological innovations as simple as putting better reflectors, more directed city lighting, can simultaneously give you the same illumination on the street for less energy, while directing a lot less of that into space. Can that compensate for the growth of human population? Probably not. Probably, as people who, in the future, people who are really dedicated sky watchers and want a dark sky will increasingly have to go to places with small population densities, and maybe high-altitude deserts will always be a good place to go. And those of us who live in cities already can see a lot less than we used to. And one can hope for improvements, but the truth is, the best we can really hope for is to not make things much worse. That already, in human terms, is progress. And on this happy note, this is bright optimism. I guess the European darkness is getting to me. I don't know, but I mean, maybe people will develop the technology to skywatch from space, and boy, that would be a view, right? If you could hop up 100 miles into the atmosphere, out of the atmosphere, to skywatch. Now that would be a view that I have never seen, and that would be exciting. So maybe that's the answer. Star parties in orbit. And that sounds like fun. That's a more optimistic topic. So on that note, I guess, thanks to everybody who participated, and apologies to those whose questions we didn't get to. And I apologize to everyone for the technical glitch. We did what we can, and thanks for hanging in there. The thread that people posted questions to will stay on, and we'll invite anybody who has ideas or comments on those to add, and the TAs and Justin and I will go through and answer as we can some of those that we have answers to. So we'll try to at least respond to those people that we haven't responded to. And again, talking to all these people and getting all these ideas from people all over the world is part of the fun of this class. And so thanks for contributing. This is great.
Yes. Yes, thank you all, and thank you, Ronan, for spending time talking with everyone. We will see you in the forums. Bye, everybody.